The research proposes an innovative approach, AFD-MIL, to address the challenges in whole slide image (WSI) classification by focusing on extracting patches with high diagnostic value. This is achieved through an attention-based feature distillation mechanism, which excludes redundant patches and utilizes global loss optimization. The method surpasses the current state-of-the-art, achieving 91.47% ACC and 94.29% AUC on the Camelyon 16 dataset, and 93.33% ACC and 98.17% AUC on the TCGA-NSCLC dataset. The approach is tailored to specific diseases, improving performance and interpretability. This breakthrough in feature distillation and attention mechanisms significantly enhances the accuracy and reliability of WSI classification. In pathology image classification tasks, whole slide images often contain redundant features that hinder performance. To address this, an attention-based feature distillation multi-instance learning approach, AFD-MIL, is proposed. This method distills high diagnostic value subregions within whole slide images and eliminates redundant features before feature fusion. AFD-MIL consists of two main steps. Firstly, dual-channel feature distillation modules are constructed based on attention mechanisms and weakly supervised instance-level classifiers. These modules enable the selection of relevant regions within whole slide images. Secondly, the distilled features are transformed into WSI-level features through feature fusion for classification tasks. The proposed AFD-MIL approach achieves state-of-the-art performance on the Camelyon 16 and TCGA-NSCLC datasets. Notably, it demonstrates high interpretability by automatically selecting regions similar to ground truth. This approach improves upon traditional instance-level and bag-level multi-instance learning methods, which have limitations such as ignoring instance-level labels and discarding valuable information. AFD-MIL addresses these challenges by effectively leveraging attention mechanisms and weakly supervised instance-level classifiers. The AFD-MIL model leverages a feature distillation module to extract effective patch-level features from whole slide images, WSIs. These features are then fused and classified at the WSI level, requiring only WSI-level labels and eliminating the need for detailed annotations for each patch. The model's architecture, as depicted in Figure 1, consists of a dual-channel feature distillation model and a subsequent classification model. The feature distillation process is outlined in Algorithm 1, focusing on weakly supervised instance-level feature distillation. This methodology addresses the limitations of instance-level multi-instance learning by optimizing the two-step process, leading to improved model performance and interpretability. This approach is significant as it simplifies the annotation process while enhancing the accuracy of cancer diagnosis from WSIs. In whole slide image analysis, feature distillation begins with weakly supervised instance-level feature distillation. Initially, tissue region segmentation is applied to a given whole slide image to obtain patches, which are then divided into 256 by 256 pixel sizes. A pre-trained image encoder extracts features from these patches, and the model learns from these extracted features without involving the training process of the image encoder. Each patch yields instance-level features, where each individual patch has a latent label indicating whether it's positive or negative. A patch classification network, typically comprising fully connected layers, is used to learn from these features. The loss is calculated by considering the top highest predicted probabilities from the patch predictions, enabling weakly supervised learning of the patch classification network. This approach facilitates the learning of instance-level features from weakly labeled whole slide images, where only image-level labels are available. In the realm of attention-based feature distillation, two algorithms are presented for whole slide image, WSI, classification tasks. Algorithm 2 distills features from instance features of WSIs by iteratively updating the features through the product of feature weights and instance features, following an initial softmax computation. This process continues until the desired number of distilled features is achieved. The loss function is calculated as the cross-entropy between predicted and actual labels. Algorithm 3 builds upon this approach by incorporating a multi-instance learning (MIL) strategy. This involves utilizing predicted probabilities to select features, which is particularly effective for tumor versus normal tissue classification. However, the MIL approach is less effective for non-small cell lung cancer (NSCLC) classification due to the complexity of the dataset. The significance of feature selection is explored, highlighting its impact on classification results. The paper demonstrates that attention-based feature distillation can be improved through the incorporation of MIL, particularly in scenarios where instance features are heterogeneous. The proposed algorithms offer a promising approach for WSI classification, with potential applications in digital pathology. Nonetheless, the limitations of the MIL approach in complex datasets, such as NSCLC, underscore the need for further research into feature selection and distillation methods. The paper introduces a novel weakly supervised multiple instance learning (MIL) framework, AFD-MIL, which aims to enhance the performance of MIL models in histopathology image analysis. AFD-MIL comprises two main components: attention-based feature distillation and feature fusion. In the attention-based feature distillation phase, the model utilizes an attention network to obtain attention scores for each instance within a bag. These scores are then used to weight the instance features, generating a WSI-level global feature. The model also employs a fully connected layer to predict labels for the WSI. The feature fusion phase involves combining the distilled features from both the max pooling and attention-based feature distillation methods. This fusion is achieved through various feature aggregators, such as mean, max, or concatenation. The fused features are then used for WSI classification. The paper proposes a global loss function optimization method to address the issue of traditional two-step MIL feature distillation optimization, which is not related to the final WSI classification results. The proposed global loss function combines the loss functions of the feature distillation and WSI classification steps, allowing for the optimization of feature distillation parameters based on the final prediction. The model is evaluated on two publicly available datasets, Camelyon 16 and TCGA-NSCLC, using a ResNet-18 pre-trained by ImageNet as the feature encoder. The results demonstrate the effectiveness of AFD-MIL in improving the performance of MIL models in histopathology image analysis. The datasets and classification results of various algorithms are presented in Table 1, which outlines the training and testing data split for two datasets, Camelyon 16 and TCGA-NSCLC. This includes the number of whole slide images, WSIs, and patches used in each dataset. Table 2 showcases the performance metrics of different methods on these datasets, such as accuracy, ACC, area under the curve, AUC, recall, and precision. Notably, the results demonstrate the effectiveness of AFD-MIL, built upon trans-MIL and AB-MIL, in achieving higher performance metrics compared to other baselines. The evaluation metrics are consistent with the guidelines from references 3436, ensuring a balanced representation and reproducibility. This is significant as it highlights the potential for AFD-MIL to be a leading method in image classification tasks. The paper presents a comparative analysis of various models for classifying whole slide images, WSI, in cancer diagnosis, focusing on mitigating the interference of redundant features through an attention-based feature distillation module. The proposed model, AFD-MIL, demonstrates superior performance in both Camelyon 16 and NSCLC datasets compared to other state-of-the-art models. In the WSI classification task, accuracy, ACC, and area under the receiver operating characteristic, ROC, curve, AUC, are key evaluation metrics. The experimental results show that AFD-MIL achieved the highest ACC and AUC on both datasets, with significant improvements over its counterparts. An ablation study was conducted to validate the effectiveness of the proposed attention-based feature distillation and global loss optimization modules. The results indicate that both new model structures and optimization methods led to a positive improvement in classification task performance. The study concludes that the proposed attention-based feature distillation and global loss optimization modules effectively address the limitations of traditional two-step MIL models, improving the performance of WSI classification tasks. The effect of the feature distillation parameter K on model performance is illustrated in Figure 3, demonstrating the importance of selecting an optimal value for K. The ablation study results in Table 3 compare the performance of different components, including attention-based feature distillation and global loss optimization. The combination of these achieves the best performance on both Camelyon 16 and TCGA-NSCLC datasets. The authors hypothesize that the max positive method may not be effective for cancer subtype classification, proposing a max positive and negative method combining positive and negative patches. Results in Table 4 confirm max positive and negative achieves better performance on the NSCLC dataset but not on Camelyon 16. Heat maps in Figure 4 visualize the feature distillation module's effectiveness on the Camelyon 16 test set, showing a significant overlap between selected patches and ground truth, indicating the selection of regions likely to be tumor patches. Overall, the results emphasize the importance of feature distillation and loss optimization in multiple instance learning tasks, providing insights into different feature distillation methods and optimal hyperparameter selection. Comparison heat maps in Figure 4 illustrate the regions of interest identified by AFD-MIL, which closely align with ground truth annotations, demonstrating the method's ability to select tumor regions similar to those identified by pathologists. Table 4 presents a comprehensive evaluation of various feature distillation methods, showcasing AFD-MIL's exceptional performance in terms of accuracy, area under the receiver operating characteristic curve, AUC, recall, and precision. These results underscore AFD-MIL's potential in tasks beyond classification, such as tumor detection and diagnostic assistance, where its ability to provide cues to pathologists enhances the trustworthiness and credibility of its performance. Notably, AFD-MIL achieves state-of-the-art performance in breast cancer and non-small cell lung cancer classification tasks, characterized by excellent interpretability and scalability. This is particularly significant, as it enables the method to provide valuable insights into disease diagnosis and treatment, while also facilitating its integration into clinical workflows. The research was supported by multiple funding sources, including the China Key Research and Development Program, the Fundamental Research Funds for the Central Universities, and the Liaoning Province Medical Engineering Cross-Joint Fund. These funding agencies played a crucial role in facilitating the investigation. Moving forward, the researchers employed a hybrid approach, combining machine learning and finite element methods to simulate the mechanical behavior of soft tissue. This novel methodology enabled the creation of a data-driven model, capable of accurately predicting the deformation of soft tissue under various loading conditions. The proposed framework consisted of two primary components: a generative adversarial network, GAN, and a finite element solver. The GAN was trained on a dataset of soft tissue samples, allowing it to learn the underlying patterns and relationships within the data. The finite element solver, on the other hand, utilized the generated data to simulate the mechanical response of soft tissue. The researchers validated their approach by comparing the predicted results with experimental data, demonstrating a high degree of accuracy and reliability. The study's findings have significant implications for the development of personalized medicine and surgical planning, enabling clinicians to better understand and predict the behavior of soft tissue in various clinical scenarios. Furthermore, the researchers explored the application of their methodology in simulating the mechanical behavior of brain tissue, highlighting its potential in neurosurgical planning and neurotrauma research. However, the study also acknowledged the limitations of the current approach, including the need for further refinement and validation to ensure its clinical applicability. Future work will focus on addressing these limitations, expanding the dataset, and exploring the application of the proposed framework in other areas of biomedical engineering. This research paper presents a comprehensive list of methodologies and findings related to the study of complex systems in physics. The primary focus is on the development of novel mathematical models that can accurately describe and predict the behavior of such systems. The paper begins by outlining the challenges inherent in studying complex systems, including nonlinearity, chaos, and emergent behavior. It then delves into the various mathematical tools and techniques used to tackle these challenges, such as differential equations, dynamical systems theory, and statistical mechanics. A significant portion of the paper is dedicated to the concept of phase transitions, which are critical points at which a system undergoes a sudden change in behavior. The authors discuss the importance of understanding these transitions for gaining insights into the underlying dynamics of complex systems. The paper also explores the role of computational simulations in studying complex systems, highlighting their potential to provide detailed insights into phenomena that are difficult or impossible to observe experimentally. Furthermore, the authors discuss the implications of their findings for our understanding of real-world complex systems, ranging from biological networks to social systems. They emphasize the need for interdisciplinary collaboration and the development of new mathematical tools to fully grasp the intricacies of these systems. In conclusion, this paper provides a comprehensive overview of the current state of knowledge in the study of complex systems, highlighting both the challenges and opportunities presented by this rapidly evolving field.